To solve that problem I raised, I'm going to introduce one more kind of object into Python, something called a generator. And any procedure or method with a yield statement inside it is a generator. So yield is a new keyword that I'm going to create here. And the idea behind a generator is I'm going to be able to control the behavior. So if I do gen test, which is a procedure here, it returns for me, as you can see, a generator object. And once I've done that, the behavior I'm going to get is the following. Generators have associated with them a next method. It's built into the Python implementation of that. And that next method starts or resumes the execution of a procedure. So inside of a generator, yield suspends the execution and returns a value. The next time I call for the next method, I will go until I get to the next yield method, in which case it will stop or suspend execution and return a value. And it will keep doing that until we run out of yield methods, in which case it will raise a stop iteration exception. So if I actually create this, I can go over to my Python system and try it. And so if I define gen test to be a procedure with a yield of 1, and then a yield of 2. And I call it, let's say I'm going to give foo is gen test. If I say foo of next, it prints out 1. It has gone until it found the first yield statement, it's returned that value, and it stopped operation. And if I call that again, it prints out 2. And if I call it again, it says, I have a stop iteration exception raised. So it's letting me control how far I go in the computation before I stop and return a value. So this just summarizes what I just did. In this case, executing the body of foo, which was something created by gentest until it reaches the first yield. And similarly to the second one. And then similarly until I get to something that raises a stop iteration exception. So why might I want this? Well, notice how I could use this. I could use it inside of a looping structure. Now this is a simple example, but it will do the same kind of idea because the gen test, that generator, is going to create something that will execute until I get to the first yield point and then return a value. And the looping construct, in fact, knows to ask that thing returned by gentest, that generator, to do that execution and then stop. And so if I were to run this particular example, it would print out each of the objects in turn because inside the for loop, it's executing until it gets a value returned, yielding, and printing it out. Great. Here's how this could be really nice. Here's a fancy operation. Let's go back to Fibonacci. But rather than writing recursive code for it, I'm going to write it in a somewhat unusual way. This is going to generate, if I wanted to do it, all of the Fibonacci numbers for me. And how might I do it? I'm going to create 2 internal variables, one that is initially bound to 0, one that's initially bound to 1. Those are the, if you like, the 0th or n-2nd and n-1st Fibonacci numbers. And then I know that the nth Fibonacci number is the sum of those. So I'm going to run through a loop that says I'm going to set next to be the sum of those 2. And I'm going to yield that value, which will halt execution until I ask it to continue, returning that value. And when it returns, I'm going to move up one step. What was the previous Fibonacci number is now the second previous one. Next is the previous Fibonacci number, and I'm going to go back around the loop. And notice there's no way to exit out of this while loop. So it will simply, if I were to call it, generate all of the Fibonacci numbers in turn. So let's try it over on my machine. I'm going to say fib is gen fib. Let me just make sure I call it. I'm going to set that up. And so I'm going to use that generator to create something. So fib is what I get by using gen fib to create a generator. And if I print out fib, you'll say it is a gen fib operation. And then I could start calling it. I'd say, give me the next Fibonacci numbers. It's 1. I call it again, it's 2. I call it again, it's 3, and then 5, and then 8, and then 13, and you get the idea. It runs until it gets to the next stopping point, yields up a value. And it's set up in that while loop to be ready to compute the next one when I need it. Funky way of dealing with it. And in fact, if I were to create this loop, which I'm not going to, it would produce all of the Fibonacci numbers until I ask it to stop, an infinite sequence of them. I don't recommend you necessarily program this way, but you can see the power of the generator because I'm separating where I stop in the operation from the overall operation I'm trying to encode. Why is that valuable? Well, generators nicely separate out the apparent computation from the actual one. It separates the concept of computing a very long sequence of objects from the actual process of getting them explicitly. And it allows you, as a consequence, to generate new objects as needed as part of another computation. So rather than, for example, generating the entire list of Fibonacci numbers and then asking for the 12th one, you could simply step through it until you get to the 12th one and then return that value. This is going to be valuable when you want to think about a way of creating things as needed. And in fact, you've seen this idea. You saw it in range. Literally what range is doing is creating something like a generator. When I say for n in range, range is returning something that gives me the first value and essentially a promise to give me the rest of it when I ask for it. I can do something with the first value inside that loop, and then when I come back around the loop again, range, that generator, will give me the next value, and so on. And this is nice because it gives us better efficiency without changing the way we think about doing the computation. I can program as if that entire sequence is available to me. The computer is going to generate it as I need it. Now, if I go back to what started this, that says that, for example, in all students, I could change the behavior. Right now, I'm returning a copy of the entire list of students. If I only have 100, no big deal. But with 100,000 or 1,000,000, I don't necessarily want to generate them if I want to do something with them on the fly or in turn. Whereas in the new version, what I could do is simply create a loop here that says, for all students in that list, just yield them up. So one at a time as I ask for them, it will give me the next one without generating the entire list as I go through them. So from this, I can move to that, and that gives me a much more efficient way of dealing with things. So what you've seen here now is how to build a hierarchy of classes with inherited behaviors, modularity to isolate changes of behaviors, classes that can have classes within their instances, and the ability to think about how I control the efficiency of all of those. And that's the power of object-oriented programming.